So in this example, we have our crate on an incline of 30 degrees, and this time we've got friction involved, and we want to know the amount of work done by the force of gravity in moving this object down the incline. Now, first thing, I didn't talk about this last time, but what we're talking about here is finding the network. Network. So let's say find the net work done in moving the object from here to the base of the incline. Now the difference here is that, let's say just for example, I have some block over here on a horizontal surface, and I apply two forces, force 1 and force 2. You can find the work done by force 1 in moving the object. Let's say the object moves here. All right, so moves from here to here. You can find the work done by force 1 by saying the work done by force 1 is force 1 times the distance d in moving the object. And then you could find the work done by force 2, which is the work done by force 2 in moving the object a displacement of d meters, say. And then your total work, or your net work is equal to the work done by force 1 plus the work done by force number 2. Or you could take force 1 and force 2 and find our net force as the summation of the forces. Here in this case there's F1 and F2 involved, so the summation of all the forces, let's say in the x direction, would be your net force would be F1 plus F2, and then the net work, and net, by net, the word net, N-E-T, we mean the total. So total, or the resultant of all the vectors. So the net work in this case is going to be the net force times the displacement. And in this case I'm not including the cosine of theta because we're going parallel to the displacement in the same direction as the displacement. So theta there would be 0 degrees, and the cosine of 0 is always 1. So I just wanted to point that out. So when talking about net work, that's the total work done. You could either sum up the individual works done by each force on the object, or take the net force, which is the sum total of all the force vectors, and then take that net force times the total displacement vector. So in this case, what we're going to go back up here, we've got a force of friction, and in this example I wanted to say let friction be 9 newtons, okay? And let our weight, well, let's assume we're going to say 10 kilogram box, so our weight is always m little g, and in that case mass is 10, g is 9.8, so we're going to have 98 newtons for our weight. Now, as always, I recommend strongly dotting in an axis system here, which is going to be parallel to, I know that looking pretty awful, parallel to the plane and perpendicular to the plane. Then we know if this is 30 degrees here, we have 30 inside there between the weight and the normal axes, the perpendicular axes to the plane or the incline. Now we've got to get the components for our weight, and we already know how to do that, at least we should. We've got the weight component going downward like this, perpendicular to the plane, and then the weight component going in the direction of the plane downward. This we always know is going to be mg sine of whatever this angle here is. So mg is simply 98 newtons, so this is going to be 98 times the sine of 30. And this over here will then be 98 cosine of 30. So now look, we've got two forces, and this the sine of 30 degrees is a half. So in this case, we've got 49 newtons. 49 newtons down the ramp, 9 newtons up the ramp from friction. Our net force down the ramp is going to be the 49 minus the 9. So our force net, our net force, our total force, our resultant force down the ramp, is going to be equal to the 49 newtons component of the weight down the ramp minus friction, which goes in the opposite direction, of 9 newtons. So our net force then is going to be 40 newtons heading in this direction down the ramp. So the net work then, just like looking what I've got here, our net work net is going to be force net times distance or displacement times the cosine of theta, but in this case our displacement d vector, let's do it in pink here, d displacement is in that direction, and notice our forces are, our net force is going to be in that direction also. So our net force is 40, and our displacement is, we didn't say, but it's going to be 10 meters. 40 newtons and 10 meters. We are going to assume for this problem that the ramp is 10 meters long. It's going to slide down the ramp 10 meters. So we can see that our net work then is 400 joules of work. Now the other way, so we use net force times the displacement for this by taking the force of the weight component minus the force of friction. But we could also calculate the net work by saying it's the work done by the weight, let's say weight is number 1, plus the work done by the friction. So the work done by the weight then is simply the 49 Newton force times the displacement, which is going to be 10 meters. So that's going to give us 490 joules of work. Work 2 is the work done by friction, and that is going to be the force of friction, which is 9 newtons, times the displacement, which is going to be 10 meters down. But now look at for this one here. The displacement is going down the ramp. The force is actually going up the ramp, so we have a force going in the opposite direction. That's the equivalent of having your force of friction this way and your displacement vector this way. So the angle theta between the two is 180 degrees, and you know that work is force times distance times the cosine of that theta. When you have the force going exactly opposite in direction to your displacement, this cosine of theta is a cosine of 180 degrees, which happens to be -1, so you would put a negative sign out in front of there. So we got -90 joules of work done by friction. Notice that friction does negative work here, and the gravity is doing positive work. So our net, or our total, is going to be the work done by gravity, which is positive, because in gravity's case, the force of gravity here is exactly in line with the displacement. Here, friction is going to be doing negative work because the force of friction here is opposite the direction to the displacement. So the two of these guys here are 180 degrees separated, and that's where the negative comes in. So if we add this plus this, we get the total is 400 joules, which is exactly the same thing here that we got. All right, so that's about it I want to say with that. So we just wanted to say that net work is the sum of all the individual works done by all of the different forces, or we can get the total combined net force down the ramp by taking the weight minus the friction gives us the total force acting downward, and then that, since it's going down and the displacement's downward, we just say force times distance to get the total work. In either case, it comes out 400 joules. Okay, so we're going to talk about energy in the next video.